Large language models, or LLMs, are highly sophisticated probability engines. They predict the next logical word in a sequence to generate text. But when an enterprise needs an AI to perform digital work, like booking flights or paying invoices, these models hit a wall. They cannot autonomously execute tasks. To force execution, engineers build API wrappers around the model. An API, or Application Programming Interface, is a set of roles that allows different software applications to communicate with each other. These wrappers act as translators, converting the model's text output into hard-coded scripts that trigger external tools. But this hard-coded approach breaks the moment the environment changes. If a software vendor updates an undocumented endpoint or slightly shifts the layout of their graphical user interface, the underlying code no longer matches the script. The automation fails completely. Solving this requires a system that does not rely on underlying HTML or API documentation. It requires an AI that can visually process a screen in real time, identifying buttons, text fields, and icons exactly the way a human operator does. This is the Large Action Model, or LAM. Unlike its predecessors, a LAM is not built for conversational output. It is engineered specifically for functional software execution. Transitioning to true agentic AI requires leaving behind text-only generation. It demands the creation of a digital motor cortex capable of direct, autonomous software manipulation. An LLM outputs discrete linguistic tokens. A LAM outputs a continuous stream of operational commands: clicks, scrolls, keystrokes, and API calls. To achieve this, the architecture relies on three distinct pillars: vision language action pipelines, neuro-symbolic reasoning, and agent ops infrastructure. Traditional robotic process automation relies on static document-object model trees. The document-object model, or DOM, is the underlying code structure that represents the layout of a web page. Because web elements frequently change IDs or structural nesting, these scripts have notoriously high failure rates. Action models bypass the DOM entirely using visual grounding techniques like uground. Instead of reading the HTML, the model uses pixel-level spatial analysis to identify a submit button purely by its visual appearance on the screen. When a SaaS platform pushes an unexpected interface redesign, the visual grounding holds. The button might move or change its back-end code, but because it still looks like a button, the agent successfully interacts with it. Robust visual perception is the prerequisite for autonomy. It provides the reliable sensory input required to pair all subsequent reasoning and decision-making. This diagram maps the core infrastructure of a digital agent, the Vision Language Action, or VLA, pipeline. It contains three distinct pathways that merge sensory input with human intent. First, the vision encoder processes a raw screenshot of a user interface. Using convolutional neural networks, algorithms specifically built for image recognition, or vision transformers, which map relationships between pixels, it compresses the visual data into spatial and semantic feature embeddings. It strips away the noise, leaving a dense matrix of interactive elements. Simultaneously, the language encoder processes the human operator's instruction. A plain text command like "generate a Q3 revenue report" is parsed into a structured planning schema, mapping out the necessary logical steps. These two distinct data streams merge inside the action decoder. By combining what it sees with what it has been instructed to do, the decoder synthesizes a stream of low-level control vectors, precise X and Y coordinates for mouse clicks, scroll durations, and exact keystrokes. A text-only HTML parser crashes when a class name changes. This multimodal fusion adapts because the visual and semantic contact remain intact, even if the underlying code is scrambled. For highly irregular edge cases, the architecture employs self-adaptive interface learning, or SAIL. SAIL allows the agent to navigate novel, undocumented software. By referencing broad interaction patterns learned from thousands of other interfaces, it correctly deduces how to use drop-down menus or form fields it has never explicitly trained on. Once an agent can reliably see and interact with any interface, the engineering challenge shifts. The bottleneck is no longer parsing the screen. It is the logic of executing complex, multi-step reasoning. Seeing the screen is only the starting line. To execute a dynamic, multi-step task, the agent requires a sophisticated reasoning layer. This is achieved through neuro-symbolic integration. The system uses neural networks for fuzzy pattern recognition, like identifying a poorly labeled icon, while relying on symbolic AI for strict, deterministic, rule-based logic. This matrix illustrates Peter Gallwitzer's Rubicon model of action phases. Originally a framework from cognitive psychology, it maps the cognitive requirements for AI system design across 4 quadrants: pre-decisional, post-decisional, actional, and post-actional. The critical moment occurs when the system transitions from the pre-decisional phase, where it evaluates various options and data points, into the post-decisional phase. Here, it crosses a discrete threshold and locks in a concrete plan. In psychology, locking in this plan requires forming implementation intentions, or specific if-then scenarios. In an action model, these are rendered as machine-readable state logic. If the login fails, then initiate the password reset sequence. The model compiles these implementation intentions into a branching action tree. This tree maps out every required step and contingency, creating a continuous sequence of executable events. Without this structured neuro-symbolic action tree, an AI remains paralyzed in the ideation phase. It generates text about what should be done, but it cannot cross the Rubicon into actual digital execution. An action model's capability scales exponentially with the size of its integrated tool library. The agent analyzes the task requirements and autonomously selects the optimal combination of utilities. For a complex data extraction, it might deploy optical character recognition, or OCR, a technology that extracts text from images, alongside data transformers and REST APIs to format and transmit the data. These utilities operate through tool chaining. The output data from the OCR tool seamlessly becomes the input payload for the data transformer, creating a continuous, automated sequence without human intervention. This diagram compares traditional infrastructure to agent-based infrastructure. On the left, a standard one-way machine learning operations pipeline is insufficient for managing cyclical, multi-tool workflows. It cannot handle loops or real-time errors. On the right is agent ops. This is the specialized operational infrastructure required for complex tool orchestration. It maintains state management to track progress and applies strict safety and enforcement protocols to bound the agent's behavior. Agent ops enables self-healing routines. When a target server times out and a tool fails, the agent automatically retries the action with an exponential backoff delay, or autonomously routes the data through an alternative API pathway. If an action chain breaks mid-execution, the system utilizes rollback capabilities. It reverts the database to its previous state to prevent partial writes and data corruption. Agent ops provides the strict guardrails and observability boundaries required to let autonomous agents execute safely inside highly sensitive enterprise environments. To see this architecture in practice, consider a complex financial operations workflow. Instead of a human team manually processing the Stripe billing and reconciliation, a LAM automates the entire pipeline. Through parallel tool execution, the agent queries the customer database while simultaneously running OCR on incoming vendor invoices. Using conditional logic, it analyzes the extracted data to make immediate decisions. If it detects a billing error, it autonomously issues a refund. If it detects a chargeback anomaly, it compiles the evidence and escalates a payment dispute. Because these actions execute asynchronously rather than sequentially, system latency drops from hours of manual human review to fractions of a second. As it resolves these tickets, the agent simultaneously generates immutable audit trails, logging every decision and API call for strict regulatory compliance. Automating a multi-platform reconciliation pipeline demonstrates a level of functional capability that predictive text generation simply cannot match. The underlying architecture is sound. The final engineering hurdle is acquiring the massive volume of high-quality graphical user interface data required to train the VLA perception layer. Scrapping static text from the internet works for language models, but a dataset of static text is entirely useless for training a dynamic execution engine that needs to learn how to move a mouse and navigate drop-down menus. This diagram shows the decentralized solution to the data bottleneck, the LAM tokenomics protocol. It creates a financial incentive structure to map human interaction. Human operators actively train the model's perception engine. By using a browser extension to record their daily tasks, they submit proof of action workflows. This provides the exact telemetry and visual data the model needs to learn specific software navigation. When an enterprise deploys one of these workflows, it consumes tokens as execution fuel. 33% of that fuel goes directly to the human creator as a reward. 34% is permanently burned to reduce supply, and the remaining 33% funds ongoing ecosystem operations. This establishes a self-sustaining, community-owned automation economy. It financially rewards the humans supplying the intelligence, completely bypassing the centralized data extraction models relied upon by major tech corporations. This decentralized economic incentive structure is the core engine generating the high-fidelity data required to advance the model's technical capability. The arrival of action models changes the day-to-day requirements of software engineering. The focus moves from code-centric development to intent-centric development. This visualization illustrates the difference between traditional oversight and intent-centric design. It contrasts the outdated human-in-the-loop model with the human-in-the-spiral framework, where human intent guides ascending, iterative cycles of agentic execution. In this paradigm, engineers spend far less time writing functional boilerplate code. Instead, they operate at the center of the spiral, architecting the constraints, defining the agent ops boundaries, and structuring the core system logic. This demands a new tier of translational expertise. Engineers must combine their deep domain knowledge with the outputs of autonomous systems, managing risk and guiding the AI through complex technical environments. We have now moved away from systems that merely predict text to systems that manage verifiable autonomous execution. The future of the enterprise belongs to the engineers who design these multi-agent systems, who architect the operational intent, and who build and ultimately govern the digital motor cortex of artificial intelligence.